Hello class, welcome to the second part of the topic of turning effect of force. In this part we'll focus mostly on what we call the principle of moments. The principle of moments simply states this, that the total clockwise moments are equal to the total anti-clockwise moments from the same fixed point in a particular system. For example, we have a diagram here of a plank with weight 1 and weight 2, and there's a pivot in between, just like what I'm having here on the table. So the distance from here to there will be D1 and my weight W1. Distance from here to here will be D2 and the weight W2, or from you it could be vice versa. From your point of view, it's the opposite. But generally we have two weights, W1, W2. We have two distances, D1 from the pivot to the weight 1. Now this direction is what called the line of action of weight 1. This is the line of action of weight 2. So for a system to be balanced, to be at equilibrium like this, then the sum of, from your case, the sum of clockwise moments should be equal to the sum of anti-clockwise moments. W1 times D1 equals to W2 times D2, as you can see there. If this half meter rule is to be balanced, then the clockwise moments should be equal to the anti-clockwise moments from the same fixed point or from the same pivot. That is the principle of moment. Let's see if we can answer a question using that. Diagram here of some two kids on a seesaw. Okay, on a seesaw, Mary's weight is 600 newtons and balances John's weight, and John is 200 newtons when Mary sits 1.5 meters away from the pivot. So how far from the pivot is John? Remember, it's like W1 is 600 newtons, D1 is 1.5 meters, that's Mary. D2, we don't know, but W2 is 200 newtons, that's John's weight. Okay, so on a seesaw, Mary's weight is 600 newtons, balances John. If you apply the principle of moments, then Mary's weight multiplied by the distance equals to John's weight multiplied by the distance. 600 newtons multiplied by 1.5 newtons equals to 200 newtons multiplied by that distance, which you don't know. So we divide both sides by 200 and 200, and we get that 900 equals to, or let's multiply 900 equals to 200 times D. Let's divide by 200, and we get a distance to be 4.5. So John should be seated 4.5 meters from the pivot, which is okay, because it shows that the lesser the weight, the further it should be from the pivot. The higher the weight, like in Mary, 600, the closer she should be to the pivot. Okay, so the lesser the weight, like John who is 200 newtons, the further he should be seated from the pivot. The higher the weight, like Mary who is 600 newtons, 3 times the closer should be. A third of the distance, and John should be 3 times that distance. Okay. Second question. Almost a similar situation. We have a plank here, a pivot, and a weight W1. We have a weight W0. Okay. So if W1 is 6 newtons, D1 is 12 newtons, what is D0? That distance. And this W0 should be equivalent to the weight. Now applying the principle of moments, then W1 multiplied by D1 equals to W0, or the 0, times D0. Okay, in this case, the D0 is 36 centimeters. So what is W0, which should be equal to the weight of this beam? In this case, you notice that there's no apparent weight on this side. There's a weight you can see here. There's no weight on this side. So at the center, where the weight is acting here by a red arrow, is the weight of this beam, which should be acting at the geometrical center. So with that principle, we work it out. 72 equals to W0 multiplied by 36. Do the division, divide both sides by 36. We get our answer to be W0 is 2 newtons. So the weight of the beam is 2 newtons, and that's the weight of the beam which is counteracting, which is balancing the weight W1 on this side. So if that's the situation that we know, if you have two weights W1, W2, distance D1, D2, and you're given a table like that and you're asked to fill in what will be the values for the blank spaces. Remember, the principle is still that W1 times W2 equals to, W1 times W times D1 equals to W2 times D2. So what will be the values of the blanks in this case? So let's fill it in. D2 will be 10, because 5 newtons times 20 centimeters is 100 newton centimeters. So 10 newtons times D2 should give you the same. That means you divide both sides by 10, you get D2 to be 10 centimeters. In the second case, we multiply 4 newtons by 15 centimeters, then you divide by 10 centimeters. You don't need to change the units here because the answers are in centimeters for distance and N for newtons, so the centimeters cancel out. That should be 6. 4 times 15 is 60, divided by 10 should give us 6 newtons. Now again, for the third row, 2 times 36 will be 72 newton centimeters. Divided by 6 newtons should give us the D1, and that should be 12 centimeters. While in the last case, 2 newtons multiplied by 100 centimeters is 200 newton centimeters. Divided by 25 centimeters should give us the value of W1, which should be, if you work it out, 8 newtons. Again, to fill this, basically it is the principle being followed that for a system in equilibrium, if what you see in the diagram there is in equilibrium, then sum of clockwise moments, which in this case should be W2 times D2, should be equal to the sum of anti-clockwise moments, which will be W1 times D1. Sum of clockwise moments, W2 times D2, equals to sum of anti-clockwise moments, which will be W1 times D1. Now, this is a real life situation. Let's assume that is nearly bridge. We have a column A and a column B, both of which are acting as pivots. Like the column on the side of the island and the column on the side of the northern mainland. We have a track passing there. Why is it that the bridge can accommodate all those vehicles and all those people passing there without breaking? That's because the principle of moments is being applied here. Let's say the weight of the lorry is shown by that red arrow is 24,000 newtons. We have on the column B, column A, we have an upward reaction force of 12,000 newtons. And that means on the column B, there should also be an equal force, 12,000 newtons acting upwards. For this car, this vehicle to be at the center of the bridge, 25,000 newtons acting downwards, it is countered by 12,000 newtons acting upwards at different ends. Again, for a system to be in equilibrium, then the sum of opposite parallel forces should be equal. The two 12,000 newtons are acting upwards. They are parallel and acting upwards. While the 24,000 is parallel but acting downwards. So, sum of the parallel equal forces are equal, and that makes it be at equilibrium and the bridge cannot break. Now look at this situation. The vehicle is at A. Okay? What happens in this case, as the lorry is having 12,000 acting down there, there should be 24,000 newtons reacting from A. So it is completely balanced. But what happens, as the lorry moves across the bridge, the equilibrium is shifting. However, the sum of parallel equal forces will be the same. So like in this case, when it moves to almost the edge of the bridge, at A, we have a reaction of 6,000 newtons. At B, we have a reaction of 18,000 newtons, summing up to 24,000 newtons, counteracting the weight of the lorry, which is acting or focused downwards. So the bridge is at equilibrium. It will not bend, it will not break. We have a third situation here. The weight of this vehicle is 4,000 newtons, somewhere in between the bridge. Now there should be a reaction column of 16,000 on this side because it's very close to that side, but less on the other side, 8,000. Whatever the case, it adds up to 24,000 newtons, counteracting the lorry weight, which is acting downwards. So let's finish up by filling up this. The turning effect of a dash is also called the dash over force. Moment is measured in dash meters. If a body is balanced, the total clockwise moment is dash to the total dash moment. A body will be dash if its center of gravity lies vertically above the dash of the body. A tractor has a larger wheelbase to reduce the possibility of its dash. Now the words to select here are toppling, anti-clockwise, Newton, moment, equal, stable, force, and base. The turning effect of a force, that's the first one, is also called the moment of a force. Moment is measured in Newton meters. If a body is balanced, the total clockwise moment is equal to that of the total anti-clockwise moment. A body will be stable if its center of gravity lies vertically above the base of the body. We'll talk more about that very soon. A tractor has a larger wheelbase to reduce the possibility of it, of course, toppling. Stability or moment bring about the second aspect, which is equilibrium, and that will be the focus of our next lesson. So for this topic, we have talked about moments, what they mean. We have stated the principle of moments. We have had a demonstration, and we have done a bit of answering of questions. See you in our next lesson.